So this video will be short because just like with area, the goal is really for you to make a formula sheet. Like, so add to your area formula sheet. I'm not making you memorize this stuff. It is about application. So what is volume? Well, now we're measuring stuff in the third dimension, right? So you would measure a straight line and say, that's 3 inches. But once we suddenly have, a rectangle going over here, it's 3 by 7, you'd say, well, length times width, that the space in here is 21 inches squared. Well, what happens when we take things like prisms, right? That we learned about uh, in our last video, or pyramids, things like that, where suddenly I'm going from a two-dimensional shape to I'm adding another dimension. I have length, I have width, and I also have a depth to these things. So how do we find the volume? Well, with a lot of them, it's easier than you think it is. Especially with prisms. Because it's really, look, you just need to find the area of the face, right? Well, the special face, the base, right? What is the area of that base? And then multiply that by how deep does it go? Because it's just repeating the area of this shape as many times as we go here. So if it's still 3 by 7, then that means that this pink area that I've shaded in is 21 inches squared. And it's 21 inches squared repeated for another, 5 inches. It's definitely not drawn to scale, but it doesn't matter. And we'd say, oh, okay, well then it's 105 total inches in here. But it's not inches squared anymore, it's inches cubed, because I'm going inch by inch by inch. I'm in the third dimension, so it's inches cubed. All right. So if two polyhedra are congruent, they'll have the same volume. Volume of a cube is an easy one because everything's the same, right? Side times side times side. And volume addition is great. So the idea that, same with like area addition, that if I can split this shape up and go, well, I could cut it off like this way, figure out what's this rectangle, and then add this one and this one. Or I could, if I wanted to, go this way and figure out this one and then figure out what's in here. So that's kind of the idea behind, look, you can split it up and just total the volumes together. So here we go. Prism, like I said, they have it as figuring out the area of the base times the height. I just think that's a little unfair just because the word base, you do kind of assume, well, doesn't that inherently mean that it's on the bottom? No, not really, because if I draw a triangular prism like this, which this is like the one thing that I'm good at, is the triangular prism. Right? Not bad. Well, here, the base is this triangle. So would you really call this the height of the prism if it's lying on its side like this? No, I think depth is a little bit fairer, or more fair. I mean, fair is definitely not a word. A little bit more fair because it'll apply all over the place. So I think it's better not to think of it as memorizing it as this formula, but to have an understanding of the concept that with a prism, I really just need to find the area of the base and then multiply that by, well, how deep does this thing go? How much am I extending this two-dimensional shape to turn it into a three-dimensional shape? With a cylinder, and we talked about this in class, how when you go from a triangular prism to a square prism, to a pentagonal prism, to a hexagonal prism, to an octagonal prism, you're getting closer and closer as you add more sides to this, the front, the base. It eventually, as you get into like infinite sides, becomes a circle, right? You actually get so many sides that it kind of becomes no sides. So you go, okay, well, the concept still applies. That with a cylinder, it's just, well, what's the area of this circle? And then how deep does it go? That's it. So pi r squared times the height. So those ones aren't so bad and are things you could probably derive on your own. The problem, all right, so here's some examples. Cylinder. I like this one because it's trapezoid. We're so used to dealing with prisms that look more like this. I go, hey, look, you just need to find the area of this, find the average of the bases. So 14 plus 6 is 20 divided by 2 is 10. 10 times the height of this thing, which is 3, that's 30. And then the actual depth of the prism is 5, so 30 times 5. Cones and pyramids. So same idea, right? Where a pyramid is really just, or sorry, a cone rather, is really just a pyramid where we go from having a square base to an octagon to a dodecagon, and we just keep getting bigger and bigger until there's actually so many sides that it turns into no sides. And so you have a cone. So you can see how these things are related to each other. It works out that a pyramid is going to be exactly 1/3 the volume of a prism that would have had the same base. So if I had instead gone like this and made this a prism, what's happening in here, this pyramid, is exactly 1/3 that volume. Exactly 1/3 of the volume. So you're still going to find the area of the base, multiply it by, well, how tall is the pyramid? But then divide it by 3. Cone, same deal. Hey, what's the area of the circle? Times how tall is the cone, divided by 3. So here's some examples. Good to pause, take a look, put these examples in your notebook. And then we have sphere. So this one's like one where I could go through how we derive it, but I think it's really better for me to just, like I said, this stuff is not, it's not my favorite chapter to teach in general because it is a lot of like, my least favorite type of stuff to teach, which is, hey, write this down and get ready to use it. But this is just plug and chug stuff. The volume of a sphere is 4/3 pi r cubed. Kind of makes sense that we're going to have r cubed, not r squared, because, oh yeah, we're in the third dimension here for volume space. And we can go over in class where in more detail where these formulas come from if you're really curious about it. But for now, for this video, I think I will leave it off here and say, get to work, do some examples, and I hope this video helped.